Okay, good morning. So we continue the lesson. I realized that the previous video was not recorded properly, so I will find the same topic from my previous lecture somewhere in the YouTube and then put the link. And then I will also hopefully upload this. Okay. So we learned about mathematical induction. I want to continue solving more examples for you today. That's it, okay? So let us start with number 2 here because we already talked about this one. Let us, for example, to refresh your memory, I want to solve this one myself and then ask you to solve, for example, number 3 and some of them to improve your skills about solving these problems, okay? So I will write down number 2 here. So we want to prove that, let me see, might be it is more natural if I solve this one first. So you remember we had this before, 1 plus 2 plus 3 up to n. We were able to find this formula using this arithmetic sum. And that was our first example to teach that I used to teach you the mathematical induction. So we have for this one 2 methods, okay? But now let me solve another one, which is of course one of the problems in the book. I don't know which one is that, but I want to prove this formula. So I want to show that if I add the squares of natural numbers, then the number becomes n times n plus 1 times 2n plus 1 divided by 6. So this is our goal. Okay, so first let me prove this, and then we go back to what I wanted to solve first. You see here, for this problem, we had 2 options. One was arithmetic progression formula, one was mathematical induction, but here we cannot use the arithmetic progression formula because these are no longer forming an arithmetic progression. This is 1, the next one is 4, the next one suddenly becomes 9, the next one becomes 25, so they are not in an arithmetic progression form, yes? So here, the formula is given to you, and I told you this is the weakness of mathematical induction. The whole formula should be given to you, and then you can prove that this is true. Okay, so this is what we want to prove. Do you remember? So the first thing that you need to do is to call this statement, for example, P of n. This statement tells you for any natural number n, this sum is equal to this expression. That is what this statement states. The first thing that you have to do is to check if it is true for the first value, n equals to 1. So what is P of 1? You have to rewrite the whole expression, but assuming that n is equal to 1. So how should I write that? The right-hand side is very clear. Instead of n, wherever I see, I put 1. But you need to have an interpretation for the left-hand side, because when you say P of n, you always start from 1 to power 2 and then add 1 unit to it, 2 to power 2, and 1 unit to it, 3 to power 2. You continue this until you reach to the given n. And then square it and then stop. But when I say n is 1, you start the process, but suddenly you have to stop, because when you start, you reach to the end. Yes, so this is the left-hand side for 1. That is the right-hand side for 1. First, you have to convince yourself that its equality is true. And this is not hard. You just calculate, yes? This is equivalent. 1 to power 2 is nothing except 1. What is the right-hand side? This is 2. This is 3. 2 times 3 times 1 is 6 over 6. And everyone agrees that this is true. So we check that P of 1 is true just by checking it. Now, the next thing is to write P of k. In your book, instead of k, I saw it they are using letter P, but I am not using P not to confuse it with this capital P, so it doesn't matter. So what k is an arbitrary natural number. Which number is that? I don't know. That is just a representative of a natural number in my head. I assume that this statement is true for that value k. So then you need to write that statement. Writing P of k is extremely simple. What you need to do is just to replace every appearance of n with the k. So this becomes 1 squared plus 2 squared plus 3 squared, and then you continue until k squared is equal to k times k plus 1 times 2k plus 1 divided by 6. This one is assumed to be true. Okay? I assume that this is true. I want to convince myself that this is also true for the next value. What is the next value? Still, I don't know because I don't know what k is. I know k is an arbitrary natural number. So the next number is k plus 1. So then I have to rewrite my statement another time for k plus 1 instead of n. So what should I do? I rewrite the statement, but I replace every appearance of n with k plus 1. So what happens? This becomes 1 to power 2 plus 2 to power 2 plus 3 to power 2. I continue this process one step more than the previous one. Here I stopped when I reached to value k. Here I continue and I stop when I reach to value k plus 1. Okay? When I reach to value k plus 1 squared, I stop. Of course, it is clear that when I go and stop here, the previous step is, which I don't write, but it is good to write it to see what is the previous one. Okay, and then I have to replace n with k plus 1. This becomes k plus 1, but don't get confused here. What will happen here, k plus 1 instead of n, another 1 added, so it becomes k plus 2. But here I have seen sometimes the students make mistakes. If you write 2k plus 1, this is not right. Yes, you have to replace the whole n with k plus 1. So this means that you have to imagine that instead of n, you are putting k plus 1, and then you have this 1 at the end. But when I multiply that, it becomes 2k plus 2 plus 1. So that becomes 2k plus 3, and then divided by 6. So this is sometimes I have seen students make mistakes, so be careful about. So you take n and you replace n with brackets k plus 1. Yes, not just by k plus 1. Okay, and then you write to be proven, yes? So this is what we still don't know. This is we assume to be true. Okay? Now you want to prove the equality. Usually it is better to start from the left-hand side of what you want to prove and try to reach to the other side. Okay? So my goal is to prove this. So I start from the left-hand side. From the left-hand side of this expression, which is 1 to power 2 plus 2 to power 2, 3 to power 2, up to k to power 2, and the next one k plus 1 to power 2. I want to calculate this. But then this is assumed to be true. So I know what happens if I add from the first to the kth term, yes? Based on this assumption, the answer to this part is this. So when I go there, from here to here, I already know the answer based on my assumption. So I take this out and put this one, which I assume to be the case, to be the same. So this becomes k times k plus 1 times 2k plus 1 divided by 6. But then after this is finished, I have an extra term here this time. Yes? And then I have to be able to simplify this and reach to what I am supposed to reach. K plus 1, K plus 2, 2K plus 3 divided by 6. Okay, at least you see that I have only one fraction involved there. So what I do, I have two expressions here and there. So this motivates me to take the common denominator to put them in the form of one single fraction. So what I do, I take the common denominator. So this becomes k plus 1, 2k plus 1, and then plus 6 times k plus 1 to the power of 2. Okay, what is the next step? Because this is not something that I can teach you. This is based on your experience that you have gained so far. So you need to look at what you are supposed to reach to, and then what you have right now. So is there any suggestions how to proceed? Yes? Expansion is probably not a good idea because you see what you are going to reach at is not in the expanded form. And on contrary, actually, it is in the collected form. So it is better not to expand, unless, by the way, this is also possible. We can call it Cajol's way, yes? So you can expand this, and you can expand that, and compare that they are the same. So if you do this, this is logically correct. So what if, because usually sometimes you are better in expanding than factoring. Okay, so if that is the case, that is no problem. So here, you expand that. You should also expand that and then compare the expanded version of this and the expanded version of that and confirm that they are the same. That is completely acceptable and logical, yes? But here, probably, if you look closer, it is not that hard, at least the next step, because you see it is in the factorized form, and then you see that k plus 1 appears here and appear here 2 times, yes? So you can factor one of them out, yes? So what can you do? So you can continue, and then I can write k plus 1. I took k plus 1 out. K times 2k plus 1 is left. And then you have plus. There were two factors of k plus 1. I pulled one of them out. One of them is still left. 6 is also left. And then I have divided by 6 here. Yes? At least this is promising. Why? Because this factor of k plus 1 that I need, divided by 6, appeared there, yes? So what I do, I probably need to continue a little bit. So here, we simplify this as much as possible. So I multiply k in, so it becomes 2k squared, and then k. And then you have 6k, which will be added to this k, becomes 7k. And then I have plus 6. And then I divide it by 6. Okay, so if we have done everything right, this part that you see here should be equal to this product. Yes, is it or not? Let us check. If I multiply this here, it becomes 2k squared. That's correct. If I multiply this here, it becomes 3k, but there is another 4k coming out later. 3k plus 4k is exactly 7k, and 2 times 3 is 6. So what you see here is the expanded form of actually this one. So you can continue. In principle, you should be able to factorize that, but I am teaching you how to cheat a little bit. If you actually understand what is going on, there is no way that these are different. You can say that, okay, if you can factorize it, factorize it. Otherwise, you can say that, okay, this one is equal to that one based on what I said. I expanded that in my head. So this becomes 2, this becomes k plus 2, and then I have 2k plus 3, and then divided by 6. Yes, did you understand what I said? So I didn't touch these two because I need them. The only thing that I have to convince myself about is that this expression that I got by this calculation is exactly equal to what I need here. There are two ways. Either you have to factorize this, or you have to expand that. I expanded this in my head, and I confirmed that if I multiply and simplify, it becomes this. If you want to factorize that, you have to be a little bit more skillful, for example, in factorizing. I can also teach you that if you want to. So this is the method that I usually use. So I ask, if is it possible that I have two numbers whose sum is 7, but this is the hard form because there are two cases. Either this coefficient is 1, which is the simple case. Sometimes the coefficient is not 1, which I will call it the hard case. So I will ask myself, can I guess two numbers for which the product is 6 and the sum is 7? I immediately find those numbers. What are they? One of them is 1, the other one is 6. Because if I multiply them, it becomes 6. If I add them, it becomes 7. So what I do, I break the middle one. Instead of having 7k, I write it k plus 6k. And then I write plus 6. Yes? Okay, then what can I do? I can take these two. So am I right? Something is missing here. Oh, sorry. The product shouldn't be 6, the product should be 12. So the sum is this number, the product should be the product of these two numbers, 12. So what are those numbers?
4 and 3.
No, but 4 and 3 doesn't work either.
You divide the 4 by 2.
No, let me see. 4 and 3 does not work here because...
And then you divide both by 2.
So...
2k plus 3.
Oh, okay, so that's my mistake. The sum, I have written 1, that's why I'm confused. You are right, 4 and 3, but the sum should be 7. I don't know why I wrote 4. The product should be 12, so that's 4 and 3. So I divide them into 4 and 3. Yes? And then between these two, you factor a k out, and between these two, you factor a 2 out. And then you see that 2k plus 3 is the common factor, you can pull it out. But this is unnecessarily long, because as I told you, you just need to convince yourself that if you multiply that, that becomes exactly the correct combination. Either you have to multiply this and convince yourself the product is this, or you have to be able to factorize this. So which method you choose, that is up to you. But by the way, the important thing for me is you to understand that this is a valid way of proving arguments. Because you might say that, okay, here we want to prove this is true, we don't know it is true, but now you suddenly say that we assume that this is to be true. It seems that it is a little bit ill from logical points of view, but I want you to understand, no, this is not the case. I am not saying that I am not saying this is true. I am saying that if this is true, there is a big if there. I still don't know if it is true. What I am doing, I'm saying if this is true, what I can show that is the next one is also true. But still there is no guarantee this is true. Because if I know that this is true, it means that I know that this is true. The difference between these two is just a matter of name of the letter that I am using. So here still I don't know it is true. I don't know still this is true. I am saying that I assume this to be true to see if I can go from this step to k plus first step. What I did here, I just showed you that if something is true for k, if this statement is true for k, definitely it is also true for the next one. But still there is no guarantee it is true for k. So how can I fix that problem? The problem is fixed by P of 1. Because when I check P of 1 manually, this is 100% guaranteed. This is true because I checked it, yes? And now I check that if this statement is true for a value of k, this will also be true for the next value. It is true for 1, so it has to be true for the next value, which is 2. Now it is correct for 2, it has to be correct for the next value, which is 3, and this continues. So there are two problems that you need to understand. First, you really need to understand why this method is working, why it is completely logical to do this. And the next thing, of course, might be sometimes hard. you'll be able to find a way to prove things. This step is the hardest step, actually. The first step is not hard. You just put them there. Yes. Is that clear? Okay. So let me go back here. So I want to wait for you so that you can. So if you don't mind, let me skip number 2 first, because of these 3 powers. You need some identities, might be you're not very good at, but let me just concentrate here. Or even simpler, I want you to do number 4. Number 4 is extremely simple. I will come to you. So you want to prove that 1 times 4 plus 2 times 7 plus 3 times 10. And if you continue this pattern, this becomes the answer. So I want you to actually do number 4 for me. Okay? Yes, Gustav? The first year I was here, I was teaching this in Matematik. Yes. That was the question. Thank you. So this is just I'm using for multiplication. Okay, you can change it to a dot or whatever you want. Okay, what happened? Could you solve it? Yes. Okay, so if you couldn't solve it, let me just explain again. It's not hard, by the way. This is a very important, very powerful tool. You're using the problem to prove the problem itself somehow. Yes. Okay, so we go here. So this is what I want to show. First of all, you see this pattern, yes? The first number here is 1, and it becomes 2, it becomes 3. So it is clear that if I continue this pattern for the first factor, it becomes n. But here, this is 4. The next one is 7, so 3 is added. The next one is 10, 3 is added again. So if I continue the same pattern, when this one reaches n, the other one reaches 3n plus 1. Yes, for example, if n is 1, 3n plus 1 becomes 4. If n is 2, 3 times 2 plus 1 is 7. If n is 3, 3 times 3 plus 1 is 10. So that pattern works. Okay? So now you want to prove it. The first thing that you do is to give it a name. So you call it P of n. And if you want, let me just explain everything. This is a statement. A statement means a declarative sentence. It declares something, okay? So you say, for all n, this expression is equal to n times n plus 1 squared full stop. So it is declaring something. This could be true or false. Here we want to show, no, it is true, okay? This is a statement P. The first thing that you need to do, you need to evaluate the truth of this for n equals to 1. So this means that you have to rewrite your statement for 1 to see if it is true or false. How should I write my statement for 1? I have to replace n with 1 and follow the pattern. Replacing n with 1 on the right-hand side is extremely simple. But replacing n with 1, you have to be careful to understand the pattern. So I have to start writing these numbers so that I reach to the value where n is the given n. But the given n here is 1. So when I start the process, it already finishes, yes? So it becomes 1 times 3. 1 times 4. Do you see that one? So I need only, so for example, let me ask you to test your understanding. If I ask you to write P2, this is not needed, but this is, by the way, extremely important for testing to test your understanding. This is a statement P of 1. Can you write the statement P of 2? You have to replace n with 2. The right-hand side doesn't have any problems. Yes, I just replaced n on the right. It is not needed. I'm just asking for making sure that you understand what is going on. Can you tell me what is P of 2 of the left-hand side? Yes, Abdul? Yes, that is extremely important. Don't think it is just the second one. Let me just make sure. So if you write just the second one, what is the answer on the left? Is 14. What is the answer on the right? This is 18. So they are not equal. So be careful. What is the meaning of these dots? It means that you always start from the first term, which is 1 times 4, and continue this pattern so that you reach to the given value for n. The given value for n is 2. So if you put 2 here, it becomes 2 times 7. 2 times 7 is the second term, but it doesn't mean you pick the second term, because this you need to interpret. Starting from 1, continuing this pattern, when I reach to the number given, I stop, not just picking the second term. So if I want to understand if P of 2 is true or false, this is not P of 2. P of 2 is 1 times 4 plus that one. Now, is it true or false? It is true again, because do you remember we calculated the right-hand side to be 18? Now, if you calculate this one, it's also 18. So P of 2 is true, not false. Because if P of 2 is false, then it is the end of the problem. This is false, yes. No. I've just told you because I want you to understand how to write P of 2. Because my impression is that based on my experience, when I ask you to write P2, you think that you have to pick up the second term. This is not correct, okay? But this is not, of course, needed for the problem. What is needed is just P of 1. Okay, so this is the first thing. And then you have to emphasize, yes, this is true. Of course, you have to check if it is true. We see that this is really true. Now, what you do, you say that let k be a natural number What number is that? I don't know. I assume that my statement is also true for value k. Then you have to rewrite your statement for value k. What is the statement? This is extremely simple from technical point of view. What you need to do is just replace n with k everywhere. That's it. So it becomes 1 times 4 plus 2 times 7 plus 3 times 10, and then it continues until I reach to k times 3k plus 1, and on the right hand side I am writing k times k plus 1 squared, and I would say this is assumed to be true. And then you have to be patient and write again what you are supposed to show to be true. It means that you need to write the statement once more for k plus 1 instead of n. Okay, what can I do? The right-hand side is extremely simple. I just take n away and replace it with k plus 1. So n becomes k plus 1. But if I replace this n with k plus 1, because I have another 1 here, it becomes k plus 2. And then I have a power of 2 there. Yes, the right-hand side is extremely simple. The left-hand side is also simple. I want to do the same thing. I want to replace k with k plus 1. So let me write here 1 times 4 plus 2 times 7 plus 3 times 10. I continue this list until here I stop at the kth level, but here I have to continue until I reach to k plus first level, and then I stop. But of course it is clear when I am doing it step by step, when I reach to k plus first step, the previous step is the kth step. And it is instructive to write it down in front of your eyes. If you write this, that is not wrong. If I just replace k with k plus 1, that is not wrong. But can you tell me what should I write if I replace k with k plus 1? I told you here, yes? Do you remember? When I say that, you need to change it with pair of brackets around k plus 1. So if I change k to k plus 1, you need to think in this way, 3 times k plus 1 in pair of brackets and then plus 1. Okay, what is the answer? 3k plus 3 plus 1, which is 3k plus 4. So if you just write this, that is not wrong. But based on the experience you have got so far, it is better to also write the previous step. So this is why I do not write this down. I will actually write the previous step, which is what? Which is this one. And then go one step further. I told you it's not wrong, but it is really instructive to see it in front of you. Okay, so first of all, let me stop here. Is there something that you don't understand so far? Okay, so this is to be proven. Yes, this is to be proven. Okay, if I ask you what are you supposed to do, you will tell me I am supposed to prove an identity. This is equal to this. Even in trigonometry, if you remember in Math 4 we learned, if you want to prove an identity, you start from one side, do the calculations and try to reach to the other side, or you do them in parallel. But if you want to choose one side, you always choose the side which is more complicated, this one. So I will start saying that the left-hand side is equal to. So let me just describe it here. The left-hand side is from here to here. But from here to here, I already know the answer. Yes? Because from here to here is exactly the assumption. So instead of this expression, which appears here again, I take it off and then replace it with this expression. So then I would write it here. So this becomes k plus 1 and k plus 2, sorry, k times k plus 1 squared. Yes? So do you remember, so what I did? I just took this off and then put this equality, put this expression, because I am assuming that these two are equal. And then I have to continue the rest. So So the lesson of induction is finished here. Okay, the rest of it is your algebra skill, so how you manipulate these expressions. It is better to have an eye on what we are supposed to reach at. So I need k plus 1, which I have here and here. So this will motivate me to factor k plus 1 out. Yes? So what happens? This becomes k plus 1. And then from this one, I have a factor of k left. But because I had two factors of k plus 1, I took one of them out. One of them is still left. But from here, only this factor is left. Yes? And now continue to simplify. I do not touch k plus 1 because I see I need it here. So k plus 1. And then I try to simplify this expression by multiplying k in. So it becomes k squared. And then when I multiply it here, it becomes k. But I have another 3k here. It becomes 4k. And then I have a 4 at the end. And I hope that you agree that they are the same, yes? Because everyone hopefully knows that this is a squaring pattern. So you can collect it back in this 4. Yes, because this becomes k plus 1. And then instead of this expression, I can write k plus 2 to power 2, yes? The first one to power 2, 2 times the first one times the second one, and the second one to power 2. And then if you compare this with the right-hand side, that they are exactly the same. So I started from the left-hand side, and I was able to reach to the right-hand side, but I was not able to do it unless I use the assumed to be true part, yes? I have to use my assumption. So this is the whole idea of mathematical induction. Yes? Is that clear? Okay, so now I want to wait for you again. We can go back here and to see if you can solve this problem. Yeah, solve number 3 now. Here. So I want you to do number 3 now. Yes?
I have a question. You know, in the previous one we did, it's divided by 6. Is it a question like that, or did you used to?
No, the question was given to me. I told you that the big days in the mathematical induction, they have to give you the whole problem, then ask you to prove it. So they gave me 6 here in the denominator. If someone finishes, you just go to number 2, because I also want to solve number 2. Okay, so if you think you understand what is going on here, don't waste your time. Go to number 2, and then we stop the lesson for today. Okay. For number 2, if you are interested, might be you need this formula. So let me write this. This is in the formula sheet. If you have a plus b to power 3, then this becomes a to the 3 plus 3a squared b plus 3ab squared plus b cubed. So this formula is also always in the formula sheet, but you might be able to use it sometimes. So here, for example, I think you will need this formula. Okay. Okay, so let me just, because I want to finalize these two, I need one more session to finish mathematical induction, that we do it after the break, okay? And this chapter will be finally finished. Let us actually solve this problem. So you are supposed to show that this is true. So what you do first, you call it P of n, for example, and then you check that this is true for n equals to 1. So what is P of 1? It is 1 squared And then when you put 1 here, this is already in the level that you have. So you start from 1 and go 2 a step at a time up to reach to 2n minus 1. But when I give you n equals to 1, 2n minus 1 becomes 1. And then when you start, you already finish. Yes? So it means that it's 1 squared only. On the right hand side, I replace n with 1 everywhere. And I need to check if this is true or false. It is clear that the left hand side, this statement is equivalent. 1 to power 2 is just 1. But if I calculate the numerator of this, it becomes 3. And the denominator is also 3. So that is yes, this is true. Yes, so the first one is true. And then what I do, I will assume that this statement is true for an arbitrary natural number that I call it k. In the book they call it little p. It doesn't matter, okay? So p of k, I assume that this is true. Writing p of k is extremely simple and you don't need to be careful for anything. You just replace the letter n with k everywhere, yes? So what happens? It becomes 1 squared plus 2 squared plus, 1 squared plus 3 squared plus 5 squared, and then you continue until 2k minus 1 squared. On the right hand side, you write 4k to the 3 minus k divided by 3. So this one assumed to be true. It's better, you need to write these things, okay, when you want to answer them in the exam. Assumed to be true. Then we show that the next step is also definitely true. So I need to rewrite my statement, but I have to replace n with k plus 1 this time everywhere. And then this becomes 1 to the power of 2 plus 3 to power 2, 5 to power 2. I continue until I reach when n becomes k plus 1. Okay, so when n becomes k plus 1, so it is 2, instead of n you write k plus 1, and then you have a minus 1. So 2k plus 2 minus 1, it is just 2k plus 1. Yes, so you continue until you reach to 2k plus 1 and then squared. But of course, now you have enough experience. It is better to write the previous step as well. The previous step is exactly this expression. Yes, so that's the previous step. And then you do what? You replace this n with k plus 1. So this is to be proven, yes? We want to prove this. Okay, so what we do, this is more or less a standard. Again, for this problem, I start from the left-hand side. But again, you see that the left-hand side is from here to here. But we already know the answer to this part. Why? Because I assume that this is equal to this expression. So what I need to do is actually writing 4k to the 3 minus k over 3 for this expression. And then, of course, you see after that I have another expression coming in. And now my goal is to be able to simplify this algebraically to show that this expression is equal to that. The mathematical induction lesson is finished here. Going from here to here is not Math 5 lesson, it is just Math 2C, how to simplify expressions. Okay, so what is your suggestion? How should I proceed? This is a little bit more complicated because it is not as before evident. At least you see that you have one single fraction here, but I have two expressions. So this will motivate me to take the common denominator. So what I do, I will take the common denominator here. This will not change at all. And then I would say that 3 will be multiplied here because my imaginary here, actually, what is the denominator here, which I haven't written down, it's 1. So 3 times I multiplied it by 3, so this becomes 3, and then I have 2k plus 1 to the power of 2. Why did I write 2? Oh yes, that's correct. I have to write, because that was power 2. Yes?
Then you factor out k, I guess.
It is not helpful. That was I was thinking, because if you factor a k out,
Then you do the conjugate with the 4.
that is good. Yes, if you want, I follow yours. Okay? But the point is that this is not in factorized form. But let us see how it goes. If you don't mind, let me just do it my way, because that is also correct. But from pedagogical point of view, I want you to understand, sometimes it is better to simplify it at some point. If you don't understand, don't waste your time to think to find the most efficient. There is no most efficient way, of course. But if you want to, you can expand that, and compare them. Okay, so might be in this case it is extremely easier, because you need to be good in factorization things if you want to continue with that. Okay, so let me just continue, and let me continue by expanding this. Let us see how it goes, because expansion is a natural thing to do. Here I have to raise it to power 2 first, and then multiply everything by 3. So if I raise it to power 2 using the squaring rule, the first one is squared, 2 times the first one times the second one, and the second one is squared, and the denominator is 3. So I haven't finished expansion yet. I multiply in, so this becomes this, and then I have minus k, and then I have 12k squared, and then I have 12k plus 3. And then I divide it by 3. I can simplify this a little bit, so I continue and stop there. Because then it is a third power, it is not that easy to factorize third powers, yes? This becomes 11k, and then, sorry, let me write k squared first to be organized a little bit. So 12k squared I write here, and then I have 11k, and then you have plus 3, and that is divided by 3. Yes? I am raising this to power 2. The first one to power 2 is 4k squared, but I have 2 times the first one times the second one, which gives me that 4k. And then I have the second one to power 2, which gives me 1. Was that your question? Yes. So I calculated the left-hand side, I reached to this one. So let me write like this. So let me write like this. I will conclude that the left-hand side is equal to this expression. I call it number 1, for example. Because this question is not that easy to guess if I can factorize it in this form. I can write it in this form. Now what I do, I start from the right-hand side also. The right-hand side is this expression, 4k plus 1 to power 3 minus k plus 1, and then divided it by 3. Okay? So what can I do here? I have to raise it, I have to expand this on as well to compare that if the answer and that answer are the same. I didn't know about that, but this formula appears here as well. So you see, I want to expand the third power here, yes? So here, I want to expand that a plus b to power 3. So what I want to do is actually using that rule here, okay? So here, this becomes equal to 4. In this formula, instead of a, I put k. Instead of b, I put 1, and then I have power 3. So I use that expansion. So this becomes k to the power of 3 plus 3k squared plus 3k plus 1. And then I have the rest of it. And then one more step, I think it will be finished. So this becomes, I multiply 4 in, and then I write minus k minus 1 divided by 4. No, why divided by 4? Divided by 3, sorry. Divided by 3, and then this means that the right-hand side is equal to, let me simplify, 12k to the power of 3 is alone, and then you have 12k squared alone, but you have 12k minus k, which is exactly 11k, and then you have 4 minus 1, which is 3, and then you have divided by 3 as well, yes? So that is the right-hand side. So you can call this number 2, and hopefully we have done everything right. You see that they are exactly identical. So you would say that comparing number 1 and number 2 gives me the equality of the left-hand side and the right-hand side. So this means finish, because my goal is to show that the left-hand side is equal to this right-hand side. The previous problems were simple, so I started from left and that just continued to reach the right. But this was a little bit more involved, so I decided to change my strategy. I simplified the left-hand side, keep it there, and then I started simplifying the right-hand side and then compare the results. Yeah, so you have to be flexible to see which one is more suitable in the problem that you are using. Okay, so I will not probably be able to finalize that problem, but this is good. If you have already, please take a note and then take it with you home. And then if you have time, you can work on it. So I will actually need one more session to finalize this, so we can use mathematical induction also to prove divisibility, so in number theory. So anything, by the way, from now on, whatever you want to prove about a natural number, one strong, powerful method is using mathematical induction. Okay, so it doesn't matter if you're studying matrices, or I don't know if you're studying number theory, algebra, even geometry. By the way, I don't know, for some reason, the level of questions in the book are extremely high when it comes to the mathematical induction. So I will probably get one more session just to practice the problems in the book, because some of them are much harder than these examples, especially level 3 problems. So if you want to have a challenge, you can also work on it. Any questions? Okay. So we end the lesson here, and hopefully you have a good time in your holidays. Yes. Thank you.